When we think about evidence in science, what comes to mind? Maybe you picture lab results, fossils, or even graphs full of data. But not all evidence is created equal. In fact, the philosophy of science explores a variety of evidence types, each playing a unique role in shaping scientific knowledge. Empirical evidence, this is what most of us think of first evidence derived from observation or experimentation. It's the backbone of scientific inquiry. For example, astronomers rely on telescopic images to study distant galaxies, while chemists measure reactions in a lab. Empirical evidence is concrete, measurable, and repeatable, but it's not without limitations. Observations can be incomplete, instruments imperfect, and interpretations biased. This is why empirical evidence must be carefully scrutinized within its context. Theoretical evidence. Not all evidence comes from direct observation. Theoretical evidence involves reasoning and mathematical modeling. Think of Einstein's equations predicting the existence of black holes long before we could observe them. This kind of evidence can guide science when direct observation isn't feasible, but it relies on the internal consistency and logical soundness of the theory itself. Historical evidence. Some fields, like archaeology or evolutionary biology, lean heavily on historical evidence data from the past. Fossils, ancient artifacts, and geological formations tell stories about events we can't directly observe. The challenge here is piecing together a coherent narrative from often incomplete data. Formal and logical evidence, mathematical proofs, and logical reasoning fall into this category. They're crucial for abstract fields like mathematics and certain areas of physics. Unlike empirical evidence, they don't depend on the physical world but instead on internally consistent systems. For example, Pythagoras' theorem holds true regardless of the universe's state. In practice, science doesn't rely on one type of evidence alone. Consider climate science. It uses empirical data like temperature records, theoretical models to predict future trends, and even historical data from ice cores to reconstruct past climates. Each type of evidence builds on the others to create a fuller picture. Here's the tricky part. Evidence doesn't speak for itself. It must be interpreted. A telescope might show us a distant star, but it takes a trained astronomer to determine what that image means. Paradigms, shared frameworks of understanding, play a big role here, shaping how we perceive and evaluate evidence. Understanding the types of evidence in science helps us appreciate its complexity. It reminds us that science is not just about facts, but about the processes and judgments that weave those facts together. So next time you hear about a new discovery, think about the evidence behind it. What type is it? How was it gathered? And how does it fit into the larger scientific puzzle?